Well, welcome to QOD video number 42. Um, Shout out to Kirkman. Okay.
Hey, where's my shout out? I don't get a shout out.
Only one per video. Okay. So the video is about what's called the common ion effect. And I'm going to read out to you what the book calls the common ion effect, and then I'm going to try and explain to you what that actually means. So here's the textbook definition of the common ion effect. The extent of ionization of a weak electrolyte is decreased by adding to the solution a strong electrolyte that has an ion in common with the weak electrolyte. So that actually would confuse me if I were in your shoes. And so let me try and explain to you a little bit more of what that means. We've actually encountered the common ion effect already with solubility equilibria and found that things are less soluble when the solution already contains one of the products of the solubility equilibrium. So this would be my definition of it. And it breaks down three ways. The ionization of a weak acid is going to be suppressed if one of the product ions of that ionization is already in solution. Or the ionization of a weak base will be suppressed if one of the product ions of that base ionization is already in solution. Or the solubility of a sparingly soluble salt is going to be even less if a product ion is already present. And that's the thing that we've already encountered with solubility equilibria. So what would be some examples of that? So common ion examples. First one had to do with the ionization of a weak acid. So nitrous acid, which is a weak acid, is going to ionize less in a solution of sodium nitrite than it will in pure water. And that's because nitrite is one of the products of the ionization. So Le Chatelier's principle essentially tells you that if there's nitrite already there, that's going to tend to shift it back toward reactants. Similarly, if I put ammonia into a solution of ammonium chloride, that's not going to ionize as much as it would in pure water because one of the products of the ionization of ammonia is ammonium. And so because that's already present, that again is going to push that back toward reactants. Silver chloride is less soluble in a solution of sodium chloride than it is in pure water, once again because chloride is one of the products of the dissolution process. If it's already in solution in some substantial concentration, that's going to push that equilibrium back toward reactants again. So let's try taking a look at this in a quantitative way. And so let's consider acetic acid. And so when we put acetic acid into water, because it's a weak acid, it will ionize partially, generate hydronium or H+ ions and acetate ions. But now instead of looking at that just in pure water, what would happen if there was already some acetate in solution? And so if we add acetate to this, or if acetate is already present when I try and do this ionization, Le Chatelier's principle says that the equilibrium will shift to the left. It will shift toward reactants. The extent of the ionization of acetic acid will be less if there is acetate already present. Or the other possibility was instead of having acetate already present, I could put some hydrochloric acid in there, which generates hydronium ions. Hydronium ions are also a product of the ionization of acetic acid, and therefore that would also tend to shift the equilibrium to the left. So let's look at a specific example of this, and we can work it out quantitatively, and hopefully I can help you see how this plays out in terms of numbers. So calculate the hydronium ion concentration and the pH of a solution that is 0.2 molar in acetic acid and 0.1 molar in sodium acetate. And remember, sodium acetate, sodium's a spectator ion, so we're really just talking about the acetate. And we know that the Ka for acetic acid is 1.8 times 10 to the minus fifth, and so we can write the Ka expression. At equilibrium, the hydronium times the acetate over the acetic acid concentration is going to be 1.8 times 10 to the minus fifth. Okay, so we have our equilibrium. Now, because the key thing to notice here is it's 0.2 molar in acetic acid, but it's also 0.1 molar in acetate. So because there is sodium acetate present, the initial concentration of acetate is not going to be 0, but it's going to be 0.1 because we've got a 0.1 molar solution of acetate. So when we construct our ice table, the initial concentration of the acid is 0.2, like it said. The initial concentration of H plus is 0, but the initial concentration of the acetate is not 0. It's 0.1. Now, because, again, Q here is equal, even though I've got a product present, I still have no H plus, and so Q is still equal to 0, and so the reaction is going to go forward. And so I can put in my X's, and then at equilibrium, the acetic acid concentration is going to be 0.2 minus X. The acetate concentration is going to be 0.1 plus X. We're going to see that X turns out to be a really, really tiny number, and so it's totally justified to make the assumption that X is insignificant compared to 0.2 and 0.1. And then the H plus concentration is going to be equal to X at equilibrium. And so we plug those things into the equilibrium concentration expression. 0.1 and X in the numerator, 0.2 in the denominator is equal to 1.8 times 10 to the minus 5. Now we just rearrange that to solve for X, and we get that X is equal to 3.6 times 10 to the minus 5, which is equal to the hydronium concentration. So if I just back up for a second, X was equal to 3.6 times 10 to the minus 5. Clearly we are justified in just ignoring it in these two expressions here. And therefore the pH is equal to 4.46. Negative log of 3.6 times 10 to the minus 5 is 4.46. So that's a 0.2 molar solution of acetic acid in the presence of 0.1 molar acetate. Let's just go back and remind ourselves what would happen if we had 0.2 molar acetic acid and no acetate, just doing this in pure water, which we've done a lot of these problems already in chapter 16. And so we start out the same way. It's 0.2 molar acetic acid, but now there is no acetate present. I've got the Ka again is 1.8 times 10 to the minus 5. There's my Ka expression. Now when we populate the ice table, it's just like we have done in the past. Both products are 0. Therefore, minus X is the change in the reactant, plus X is the change in the two products. And we assume that this number is going to be sufficiently small because actually in this case we would have to go back and do the initial concentration of HA divided by the value of K to make sure that it was more than 400, but it is. And so we can ignore X and just say that at equilibrium the acetic acid concentration is 0.2. We've done these problems before. We plug those equilibrium values into the Ka expression. We solve for X. It comes out to be 1.99 times 10 to the minus 3. And that again is the H plus concentration. Therefore, the pH is the negative log of that, which is equal to 2.72. Where this becomes really sort of where the rubber hits the road and where you can kind of see what's going on here is to compare the two results. Okay, so here's the summary of those two different sort of experiments that I just went through. If I just have a 0.2 molar acetic acid solution, it ionizes about 1%, and the pH at equilibrium is 2.72. If I've got a 0.2 molar solution of acetic acid in the presence of 0.1 molar acetate, you'll see that suppresses that ionization quite a bit. Instead of ionizing by 1%, it only ionizes by 0.02%. And the pH instead of 2.72 is 4.46. And remember that every pH unit is tenfold. And so what this is saying really is that this solution here has about 50 times as much H plus in it as this solution does. And so this is the idea of the common ion effect. If I have acetate already in solution, it significantly suppresses the ionization of the acetic acid. So that's the summary of what we've seen so far. Now let's go on to the super executive summary of everything we've talked about up to this point. when a weak acid is placed in solution with its conjugate base, or vice versa, a weak base is placed in solution with its conjugate acid, the equilibrium concentration of each species is essentially equal to its initial concentration. And we just saw that, this is the big takeaway from the common ion effect, that in the example we saw where the acetic acid and acetate were in there together, the change in concentration of the acetic acid between the initial condition and the equilibrium condition was so tiny that it can essentially be ignored. And the change in concentration of the acetate between the initial condition and the final condition, equilibrium condition, is so tiny that it could also be ignored. And so we can simply treat the equilibrium concentration of both the acid and its conjugate base, or weak base and its conjugate acid, as being equal to the initial concentration. Okay, and this makes it super easy and also super duper fun to calculate the pH of a buffer solution, which of course has you now asking the question, wait, what's a buffer solution? And so a buffer solution is, no thanks to the peanut gallery, a buffer solution is a solution that contains both a weak acid and its conjugate base, or vice versa. So the example that we were looking at earlier, in which we had acetic acid at 0.2 molar and acetate at 0.1 molar, is an example of a buffer solution. And so what I'm going to do now is just very quickly go through the derivation of what's called the Henderson-Hasselbalch equation, which makes it really easy to calculate pH as a buffer solution. So if we just consider a generic acid that up to now, we've been calling a generic weak acid HA, it's going to ionize in water to give you hydronium ions plus A minus, which is the conjugate base. And we can write the Ka expression of that is that Ka is equal to the hydronium ion concentration times the A minus concentration over the concentration of the weak acid, the equilibrium concentration of the weak acid. Okay, now we can just rearrange that equilibrium constant expression to solve it for Ka. And so we do that this way. Ka, once again, is equal to, all I've done is just taken this hydronium ion concentration and sort of pulled it out of the numerator and set it next to that fraction. Now I'm going to take the negative log of everything. So I'm going to take the negative log of both sides. I get the negative log of Ka is equal to the negative log of the hydronium ion concentration plus the negative log of the conjugate base species present, the weak base species present over the weak acid species present. Okay, that negative log of the Ka is what we call the pKa. And it's simply taking the negative log of the Ka. And so that's easy. If the Ka of a particular thing, say acetic acid, is 1.5 times 10 to the minus fifth, then the pKa is equal to 4.74. I happen to have that memorized. Negative log of hydronium concentration is pH. Okay, this is the weak acid that's present, and this is the weak base that's present. All right, we can just slightly rearrange that now, or just rename these things, pKa and pH, and say that pKa is equal to pH minus the log of the base concentration over the acid concentration. And we can just rearrange that one more time to get pH isolated. And that becomes pH is equal to pKa plus the log of the base concentration over the acid concentration. And this is what is known as the Henderson-Hasselbalch equation. And this is what makes it really easy to calculate the pH of any buffer solution. So let's do a quick example, and then I'll put some more examples of this into the suggested problems prior to the QOD. And so let's take lactic acid. What is the pH of a buffer that is 0.12 molar in lactic acid and 0.10 molar in sodium lactate? And lactate is the conjugate base of lactic acid. And the Ka for lactic acid is 1.4 times 10 to the minus fourth. And so this gives us that problem by giving us the concentration of lactic acid and giving us the concentration of lactate. That gives us the numbers to plug in here. The only thing we need to do to calculate the pH is to calculate the pKa, which is simply the negative log of 1.4 times 10 to the minus 4. And so the pH is equal to the negative log of 1.4 times 10 to the minus 4 plus the log of the lactate concentration, 0.1, over the lactic acid concentration, 0.12. Negative log of 1.4 times 10 to the minus 4th is 3.85. The log of 0.1 over 0.2 is negative 0.08. Therefore, the pH of that solution is equal to 3.77. And we can use this for any example of a buffer, and we'll talk more about buffers. We'll spend more time talking about buffers even after the test. What I really wanted to do was just talk about the common ion effect and get into a Henderson-Hasselbalch 1 calculation, just so that you understand how to do it and how easy it is to do it, and then we can move on from there. So that's the end of the video. I will have suggested practice problems for you to do. This is only 16 minutes long, so now members of the peanut gallery can come over here and shout into the microphone if they want to. Okay, that was as much as I got. All right, see you later.